welcome everyone to the session Wearable Robotics and Micro Robotics. Our first speaker for this session is Marwa ElDiwiny. She's a PhD student from BUB University. And today she will share her research with us about designing and modeling soft IEAP artificial muscles. The floor is yours, Marwa.
Thanks so much for this introduction. And again, I'm pleasure to be with my mentors and everyone here. So I'm honored to be with you guys. Thank you. So I'm going to present today a work I did 2 years ago about modeling and design of soft ionic conductive polymer as artificial muscle. So as you may know, soft robotics is still maybe a hot topic, and we have a lot of question going on in the field and limitation. So today I'm going to speak about smart material that can actuate and sense at the same time. So before that, we go that, as you may know, in soft robotics, the biggest inspiration we have from the nature. So we can see here the example of chameleon or octopus or sandfish or molluscopper. So all these examples, when we look to the inspiration for that, either the shape is changing, they can change the shape. If we see the chameleons, they have this amount of force they can produce to catch the prey, or maybe the locomotion itself. So all that's inspiration, and we have a lot of questions going on in the field, how we can design materials that can have this kind of forces produced or displacement, or they can change the shape and also produce the desired mechanical performance. So in the state of the art, as you can see in soft robotics, we have a variety of materials. And one of the materials we have either could be like elastic rubbers, for example, massive material. And in the other side, we have, for example, smart material. And for me, I'm a big advocate for smart material. And I tell you why. There's two approaches in the field. Either we can use, as I said, elastic rubber, for example, to use it for different application, either in industry, for example, the gripper, as you can see in Soft Robotics Inc. However, I believe that if we wanted to design like embodied intelligence, so that we have a material that can actuate and also can have this kind of computation and also sensing what is happening. And if you ask me what's kind of material so far in the field we have that can do that, it's ionic conductive polymer. However, there's a huge limitation in this material, and that's maybe caused a little bit frustration in the field, that how we can close this trade-off, or how we can enhance these properties and gain all what we want in the material, so that we can, if we want to replace, for example, servo motor, one of the question, how we can design soft material that can have this mechanical performance and also have low energy consumption. So when we look to the research gap, or what kind of the missing pieces we have, when it comes to material design. So we wanted materials that have sufficient mechanical performance, also high response time, and can also operate at low energy, and also reproducible and have biocompatibility. So that's the corner we wish to have in the field. However, there's still in the field this kind of, if we achieve something in the material, there's something still missing. And that's something we still in the field will figure out how we can solve this. What are the tools we need to close this gap, so that we can achieve what we dream of, that kind of material that can be used in different applications that we aspire to have. So when we look to the soft material, especially here, what we call a smart material, we call it a smart because it can actuate itself as well. When we apply voltages, for example, in that case, you can get this kind of mechanical performance, and also can be used as a sensor. So what's really beautiful in ionic conductive polymer, it can be used as actuator and the sensor at the same time. And that's, of course, if you can imagine, we want to design any kind of passive material, you have to you have to be bothered sometimes how I can design the sensor, how I can embed the sensing and network in the material. So that's another approach. But when we look to the smart material, when it comes to ionic conductive polymer, there are two types. The first one is ionic conductive polymer, and the other part is called dielectric elastomer or electronic EEBs. And there's different categories of materials. You can go either for ionic or electronic EEBs. So basically, for people just to know what is the difference, ionic conductive polymer is based on the electrostatic interaction between the ions stored in the material and the voltage applied. So it's electrostatic interaction. However, on the other side, when we look to dielectric elastomer, it's different mechanism, but we can see the huge difference we have here, the voltage applied. Any conductive polymer operate at 2 volt, however, at electronic AEBs operate like 1 kilovolt. Of course, it doesn't kill you, but it's high voltages. And what's the trade-off we can see between ionic conductive polymer and electronic EB, that the force produced. There's a trade-off here. So here we have low energy applied, but the forces when we see an ionic electroactive polymer in micronewton scale. And if we look to EBs, of course, we can go to Newton scale. So that's the trade-off, the voltage applied and the mechanical performance. So that's still missing pieces here. We're still missing question how we can combine both of them. We're still not there yet. But I wanted to go for how we can design EIP and what's actually lead to what we can improve and what is the tool we can use. So AIB, for example, here, you can see in this video here, we have 3 layers. It's like a sandwich. So we have 2 conductive material, and in between we have dielectric material. And the idea is when we have this kind of, it could be more than 3 layers. You can design 4, 5, and the more you design, more you increase number of layers, it could increase the forces. But firstly, how it work? If we look to the EIB, we have a sandwich layer, so we have 2 conductive material, and in between we have dielectric material. And we have this kind of this structure. We have the operations called osmosis, where the ions is stored in the dielectric layer, which is in yellow. The ions is stored in this layer in between. And once we make sure that the concentration of these ions, of course, in the lab, you can control even how this, the positive and negative, the cation and anion, you can control that in the lab, how the size of this ion should look like. Why? Because this size of ions, as it's the name, ionic conductive polymer, the size of ions is so significantly contributing in the amount of force produced. So imagine that you make sure this ions is filled completely and the concentration is consistent in this yellow layer. Then you take it and you can apply the voltage. And when the voltage is applied, the electrons is moving in the conductive layer, the black one. Here's the operation is happening. The positive and negative is kind of electrostatic interaction. So imagine that we have the cation is, for example, is much bigger so in size and the radius. It means that it can move. It just stuck. This material has a polymer network chain, so you can imagine it's like a chain, and you have the positive and negative, and you have the electrons moving in the both sides. So if the cation, for example, is much bigger, it means that it can't move. If there's a force attracting it, it doesn't move because it's just so big. However, on the other side of the anion is much smaller, and there is attraction or repulsion on other sides, it can move freely. So that's make it either bend in this direction or in this direction. So that's something you can do in the lab. What the size of the ions do you need? That's something very important at the lab to make sure that how the bending is happening and in which direction. So as you can see, it's quite challenging to feel how we can do this characterization. So when we apply the force, what kind of test we want to see? And there's one of the tests is called the block the force. So we clamp the sample, and clamping is so important when it comes to soft material. It's so important that we need how we do this characterization properly. So what we do here, we have to measure the block force and displacement for the sample. And what's really interesting here that we want to make sure that the places we select over the special domain of the sample. So we can see that the sample here, we apply this prop and actuated the sample to see how much force it could resist in the bending, the forces applied by the material. And what is really fun about this material, because in the soft robotics field, we speak about how we can design the material has stiffness changing. And that's something very interesting in the field. So either you can use multi-material with either elastic one and stiffer one, so that we can have this multi-material, and we have this kind of stiffness variable material. And that's what already we have in nature. We have this kind of variable stiffness, so that we can control different behavior or displacement. However, in ionic conductive polymer, when we do this test, if you can see the stiffnesses here, it's different. When we go to different spaces, for example, from the clamping point to the length of the sample, when we move from the clamping point, we can see the stiffness is decreasing, is decreasing. Yeah, so from the clamping here, we can see the stiffness is much higher. And when we go to the tip point, the stiffness is decreasing. And the same for the force produced. We can see the forces is much higher near the clamping point and then is decreasing. And that's a question, why does this happen like that? Why is this bending behavior happening in this material? And all that for free. You don't have to use tendons or cables or anything like that. And why it's happening like that? What is the reason for that? So the test we do that, we, as you can see, the sample is clamped here, and we select 2 points. The first point is 5 millimeter from the clamping point, and the other one 9 millimeter from the clamping point. And the length of the sample is 10.76 millimeter. And we can see when we see how much the force is produced. So you can see that the force near the clamping is much higher. You can see it's around the maximum, the steady state value for the force is around 1,535 micronewton. And the response time is 2.5 seconds to reach this value. And when we increase the voltage, we can see this the value of the force is increasing. So when we apply at first step, we apply 1 volt. So we have this kind of force at this distance, 1,535 micronewton. And when we increase the voltage, the force is increasing at this point, and the same response time. And when we increase 2 volt, sometimes there's no consistency. Sometimes it's due to the noise. And we do the same at 9 millimeter. Also, we see that the force is increasing, but the point is, what is the reason behind that? If we, what if we increase then more 2 volt? Sometimes the sample is damaged, and that's very interesting, that we can't increase the number of voltage beyond 2 volts, the maximum is 2 volt, and the forces is increasing directly with the voltage applied. However, one of the questions that why we have this kind of behavior. So we can see this force is non-linear, and sometimes it goes to saturation, and sometimes it doesn't go to saturation. So there's a lot of questions here. Why is this happening? And to answer this question, maybe we need modeling. So I think one of the things is that missing in ionic conductive polymer, why we have this kind of behavior in the forces. So we have this nonlinear response and then saturate, and sometimes it doesn't saturate. And if we apply more than 2 volt, sometimes the sample is damaged. So why is this happening? So to explain that, I think that depending on the application, if we need a certain forces applied and the displacement. So what is actually we need to consider here if we wanted to incorporate ionic conductive polymer in, for example, biomedical application like the cochlear implant, to have like undulation motion or bending behavior. So we have the friction and the masses here, but how we can anticipate what kind of shape, what kind of forces do we need? What kind of displacement we need for this application. So here, there is a point about how we can correlate the electric voltage applied with the mechanical performance. And here we propose this stress charge coupling, and how we can see this transition from the electrostatic interaction to mechanical performance. So I think here, that's a point, which direction we have to go to when it comes to modeling. Should we go to, for example, just a couple empirical data? Is it enough? In the case of any conductive polymer, it is not really accurate, because as you can see, when you do this in the lab, there's a lot of noises going on. You need to make sure that the result is reproducible. So it doesn't really touch about what is actual physics happening. So when we go here, we apply that one-dimensional diffusion model. So when the voltage is applied to the sample, we apply a diffusional model in one direction. And then using the stress charge coupling, what we propose here, taking into account the area and the thickness of the sample. And what we found that when we increase the thickness of the samples, the forces increase. However, the response time is decreasing a little bit. So it's not really fast enough. And that was a trade-off about the thickness and the response time. So that's something still we don't know how we can anticipate or how we can make sure that both items meet each other. But when we apply this technique, the proposed stress charge coupling, we can predict the final elicited value and what kind of geometry do we need and what kind of thickness also in this operation like that. So that's the result for the bending stress and force. And also here, as a strain. So when it comes to simulation, we use the SUFA framework here, and as you may know, the SUFA is based on FEM. However, when it comes to ionic conductive polymer, one of the feature is missing here. If you can see from the empirical work here, this kind of this rise time and this non-linear behavior happening here. Sometimes it's hard to capture when it comes to simulation. And because ionic conductive polymer is highly nonlinear material and anisotropic, so when you try to do that in SUVA, for example, which is based in linear FEM, it's hard to converge a solution. So you can't reach the final value of the force. And this is something still also on the simulation tool we can't really simulate nonlinear material. However, now I'm using for other project FreeCAD, it's open source and you can somehow simulate nonlinear material. However, in general, we still have this kind of tools that can capture the physics happening when it comes to this behavior, the nonlinear behavior and simulation tools. That's something still missing. And yeah, so I think that's also open questions for simulating smart material. And now we are trying to, that's something we did about how we can couple different ionic conductive polymer to achieve different actuation principle. So, but still, as I said, I think the field is still in its infancy. So although it's really old, but this is kind of question how we can couple different actuator, to achieve, like in this case, we wanted to couple 2 or 3 actuator to manipulate something or actuate something. So what I think is still missing here, I'm still working in the modeling and simulation. In other project, we try to use also self-healing material. So that's something also part of the work, how to model them, and either in physics-based modeling, and also in simulation tool, how we can capture this physics happening in nonlinear material. So I think that's a sneak peek about what we're doing in, when it comes to modeling and design of smart material. I don't know if you have any questions. I'm happy to answer if anyone have any questions. And thank you for time.
Thank you a lot, Marwa, for sharing your research with us. It was really interesting and insightful. Thank you very much.